acceleration, and that's how we define gravitational acceleration, and we saw that gravitational acceleration is going to be constant at the surface of the Earth because well, all these quantities are going to be constant. G is constant, and E is constant, and R is constant, so that's why G is going to be constant. And we can also calculate G at any given point above the surface of the Earth because the radius is going to increase. So that's how we're going to calculate the gravitational acceleration. Also, we define the gravitational potential as U is equal to negative GMEM divided by R, and we basically what we did was we calculated that using the definition of U, and we basically proved it by taking the integral of the force with respect to R. And then we looked at the motion of the satellite. We also explored the three laws that Kepler introduced, Kepler's law. And that was for chapter 13 that dealt with gravitation, and we did also some problems with that regard. Now, a multi-constant question on the electric fluid is going to change as well, and that depends on that, if the, because, and you've seen that, if you basically put your thumb over the garden hose, what's going to happen here is the velocity is going to increase because the cross-sectional area that the fluid is coming out is going to decrease. Any questions? Okay. The last part of this chapter is Bernoulli's equation. It's basically, it looks kind of like what? Exactly. It's a conservational law basically. So here is, what is the conservation here? Well, each conservation of pressure, very good. Each term represents pressure. So this is pressure, this is pressure, this is pressure. So all these pressure. So pressure is going to change when the height changes. Pressure is going to change when the velocity changes. So here we have some kind of a conservational law that shows us, Bernoulli equation is showing us that, if in a fluid flow, if the velocity changes, if the height changes, how the velocity of the fluids coming out of the pipe is going to change. So this is going to be again, a very important equation that you can use. So Bernoulli equation and buoyancy is the two main equations and two main topics that you have to remember from this chapter. Okay? Yes.
This might be beyond this chapter, but I was just curious. Wouldn't buoyancy be affected eventually? Like, let's say with a basketball submerged under, and if you put it in deep enough, it'll crush, right? With the pressure of the water.
Well, yes. If you put the basketball, just basically
like a deflated basketball.
Deflated, yeah. It gets, well, it just gets smaller. The volume of it is going to change. Yes. But here is we're basically assuming that we're not going to have that much depth. We're not going to put the submarine all the way to the bottom of the ocean. We assume that the bottom is worse.
There we go. Much better.
Okay, everybody can see this. So M aluminum is going to be equal to M lead. So now we have to express the mass of the aluminum in terms of the volume of aluminum and the rho of the volume. So here is rho. So what is rho? Rho is equal to mass over volume. So if you want to find mass is going to be equal to rho times V. So what I need to do here is now I say rho aluminum times V aluminum is going to be equal to what? Rho lead times V lead. So the rho aluminum, what is rho? It's a constant. Okay? What is V aluminum? V aluminum is the volume of the sphere. So volume of a sphere is what?
4/3 pi r cubed.
4/3 times 4/3 pi r aluminum cube is going to be equal to rho lead times 4/3 pi r lead cube. So what cancels? 4/3 cancels 4/3, pi cancels pi. So what you have is we can have a ratio of rho aluminum over rho lead okay? Here you go. Here comes the,
Thank you.
okay. So let's just make it a little bit bigger. Can we see it?
No,
Can we see it?
no.
So make sure you
Get it. Aluminum is 2.7 times 10 to the power 3 kilograms per meter cube.
if you
2.7.
We plug in 11.3.
So the best thing to do is simplify this in terms of what? Symbols.
It's gonna cancel out. Because we're doing the ratio.
What is equal in this problem? Mass. So set the two masses equal to each other. Mass. We have to express masses in terms of
Row and volume.
So
density and volume. There you go. You got it. That's it.
equal to m over.
And then you simplify everything. Too much. Too fast. No. They're ones that, sphere, so yeah.
How's it going over here, guys?
It's
going.
It's going?
volume of a sphere is what?
Oh, no, man.
Because you know things. You're the female in the group, which means you're smarter than we are. So you have to know these things.
Facts.
Facts.
How's y'all's going?
Okay, so density.
It's going.
It's going? I've gotten that answer a lot, surprisingly. I guess that's pretty good in a physics
Same
class.
point. So you said density times volume.
Same mass too,
They
right?
have the same mass. Mass is equal to
The only thing
density
different is the
times
volume.
volume. You said.
So we need to know the ratio of the radiuses, right? So
Y'all are working. I won't interrupt y'all.
So r cubed and 3m over no.
R is equal to the cube root
4 pi times. Alright, the left side is radius L and the right side is radius A. I forgot that way.
Then when you're done with that, don't come
Yeah, let's come see how these guys are doing. Bad kids.
So wait.
Did you get NA for student? Yes, I did. Well, no, cube roots. You can
You cancel the things, you can break them
cancel
apart.
anything equal within the cube. Because it's just raised
Yeah, that's what I'm saying. So 4 pi times 2.7.
How are you guys?
Right?
How's it going over here? Sneak a peek? Anything? Anything happening?
Should I start writing?
Should you?
I don't know.
Are we doing good over here?
It's like, I'm slightly confused because the pi and the r cube will cancel out if you divide.
Well, the odds are different, so I was trying to find the ratio. It's not gonna.
it's R1 and R2.
Okay.
What was it now?
And he basically said there are structures that are much which means that they could rotate every single creating no entity loss or so that's the creating entity.
So divide by top line.
It's a physicist at first, but acting for it is really, he says no.
Gets rid of the pi.
Pi's gone for.
Right. How about the interwebs kids?
How about them? There's only 6 people online today.
Why is nobody in class?
I don't know. I don't know. I guess they figure finals are almost here. They're done.
Yeah, really. I don't know if I should be talking, but I'm going to. So.
Why not? Do whatever you want. You're making it. Yeah, normally we have more people than this.
Yeah, jeez.
Because
Where's Kevin?
we want like.
There's no online activity.
They're
there's a
gonna
little
start,
bit.
yeah, there's a little bit, they're starting. Ask them to.
Where's this answer that appeared? The 636?
That's the answer to part A.
Oh, this kid.
We don't want to see that though, we want to see the work.
Yeah.
Right.
This is a cool screen. It's true.
Don't forget to convert
Like, you can zoom in.
Nice.
Read
the
the
units.
words.
Nice.
Good on that guy.
Yeah.
We have the same one over here in our command center. Have we had any online activity yet?
Doesn't look like it. Check my other room.
Oh,
Yep, JP. 1.6.
oh, there we go. 1.6, is that right?
Let's see. Yeah. Do you want to?
I got 1.6.
Okay. Do you want to?
Yeah.
How is it over at Central Command?
Here's the good room. I have
There's
the
no.
lazy room. Kevin Allen.
There we go. Yo, Kev butt. Still just that one guy?
He didn't start part B yet.
Huh. Are they supposed to be putting their work?
Isn't putting it down here.
Are they supposed to be putting their work on the online?
I mean, this is what a typical private classroom looks like. That's slightly good. See, they drew those arrows there.
Cool.
They were talking here.
Well, I could tell you.
They're at least interacting.
They're interacting. So this was some good talking. But talk was better.
Well, it says the cylinder of oil is 75 centimeters. Yeah. We're assuming the wood is on top.